There's something peculiar about genius that most people misunderstand entirely. They imagine it as a kind of gift, something you're born with, a spark of brilliance that separates extraordinary minds from ordinary ones. But if you examine how actual geniuses think, how they approach problems, how they reason through complexity, you find something quite different. You find a method, a discipline, a way of forcing the mind to work that anyone can learn. Let me ask you a direct question. What is thinking? Not the automatic kind, the reflexive pattern matching your brain does constantly, but real thinking, the kind that produces genuine understanding, the kind that reveals nature as it actually is rather than as we assume it to be. Most people never truly think in their entire lives. They recognize patterns, they apply formulas, they remember solutions, but they don't think. The greatest physicists in history didn't just solve problems, they reconstructed them from the ground up, stripping away every assumption until only the bare physical reality remained. When approaching quantum mechanics, they didn't start with existing formulas. They started with the simplest possible question: how does light actually interact with matter? Then they built upward, step by step, checking each logical connection, until the mathematics emerged naturally from physical intuition. This is not how most people approach intellectual work. They start with conclusions and work backward. They memorize techniques without understanding foundations. They accept authority without verification. Their brains become filing cabinets of disconnected facts, rather than engines of genuine comprehension. But here's what's remarkable. The difference between genius-level thinking and ordinary thinking is not intelligence. It's method. It's a trainable skill. And the first step is understanding what actually happens in your brain when you think properly versus when you merely perform cognitive reflexes. Consider a simple physics problem. A ball rolls down an incline. Most students immediately reach for equations, kinetic energy, potential energy, Newton's laws. They plug numbers into formulas and get an answer. But do they understand what's happening? Ask them why the ball accelerates, and they'll recite memorized phrases about gravitational force. Ask them what gravity actually is, and the understanding evaporates. Now watch how a true physicist would approach this. They'd start with the observation. The ball speeds up as it descends. Why? Because something is pushing it. What's pushing it? Gravity pulls it downward, but the incline constrains its motion, so the gravitational force splits into components, one perpendicular to the surface, one parallel. The parallel component accelerates the ball. But why does gravity pull at all? Because space-time curves near massive objects, and objects follow geodesics through curved spacetime. Each answer opens a deeper question, and the understanding builds in layers, from observation to mechanism to fundamental principle. This is first principles thinking. It's not about memorizing facts. It's about reconstructing reality from the most basic truths you can verify. And your brain resists this process intensely because it's metabolically expensive. Pattern matching is cheap. Real thinking burns energy. Evolution optimized your brain for efficiency, not truth. Here's the physiological reality. When you recognize a familiar pattern, your brain uses established neural pathways. Signals travel quickly through myelinated connections. You experience this as fluency, as ease, as understanding. But you're not thinking. You're remembering. When you actually think, when you force your brain to build new logical connections, to question assumptions, to derive conclusions rather than retrieve them, different neural networks activate, the prefrontal cortex engages. Working memory strains under the cognitive load, you experience confusion, difficulty, frustration. This discomfort is not a sign of failure, it's a sign that actual thinking is occurring. The problem is that your brain interprets this discomfort as a signal to stop. It wants to return to the ease of pattern matching, so it offers you shortcuts, familiar phrases, memorized formulas, conclusions that sound right. And most people accept these shortcuts gratefully because they relieve the discomfort. They mistake fluency for understanding. Genius-level thinkers have learned to distrust fluency. When something feels too easy, too obvious, too familiar, they become suspicious. They ask, do I truly understand this, or am I merely recognizing a pattern? And then they do something that separates them from everyone else. They deliberately strip away the pattern and rebuild from fundamentals. Let me give you a concrete example. Everyone knows that light travels at 300,000 kilometers per second. That's a fact. But what does it mean? Why does light have a speed limit? Most people never ask this because they've accepted it as a given, a brute fact of nature. But there's no such thing as a brute fact in physics. Every phenomenon has a mechanism, a deeper explanation. Maxwell discovered that light is an electromagnetic wave, a self-propagating oscillation of electric and magnetic fields. The speed emerges from two fundamental constants, the permittivity and permeability of free space. These constants determine how electric and magnetic fields interact, and when you combine them mathematically, out pops the speed of light, not as an imposed limit, but as a natural consequence of electromagnetic properties. But why those particular values for permittivity and permeability? Now you're asking about the structure of space-time itself, about the fundamental constants that define our universe, and this is how genuine understanding develops. Each answer reveals a deeper question. Each layer of explanation connects to broader physical principles. You're not memorizing facts anymore. You're seeing how reality fits together. This is what your brain can do when you force it to think like a genius. Not through raw intelligence, but through disciplined method, through systematic refusal to accept surface explanations, through constant questioning of assumptions, through rebuilding everything from the ground up. The question now is practical. How do you actually train your brain to operate this way? How do you override the deeply ingrained tendency toward pattern matching and force yourself into genuine first principles thinking? Start with this exercise. Take any concept you think you understand. Anything. Gravity, evolution, electricity, democracy. Now explain it to yourself without using any technical terms. Only use words a 10-year-old would know. You'll discover immediately how shallow your understanding actually is. When you can't use specialized vocabulary, you can't hide behind memorized definitions. You have to explain the actual mechanism, the real physical or logical process. And most of the time you'll find you can't do it. You know the words, but you don't understand the reality behind them. This is a powerful technique used by the greatest scientific minds. The principle is simple. If you truly understand something, you can explain it in simple language. Not because the concept itself is simple, but because genuine understanding means you've traced it back to fundamental principles that are simple. Complex jargon often masks incomplete understanding. But here's what's crucial. This process feels terrible. Your brain will fight you. It will offer you technical terms as shortcuts. It will insist that some things are just too complex to explain simply. It will generate frustration, confusion, even mild anxiety. These sensations are not signs that you're doing it wrong. They're signs that you're doing it right. You're forcing your brain out of comfortable pattern matching and into actual cognitive work. The neuroscience here is straightforward. Real learning, the kind that produces flexible, transferable understanding rather than brittle, context-dependent memory, requires synaptic plasticity. Your brain needs to form new connections, strengthen weak pathways, integrate isolated facts into coherent networks. This process happens primarily when you struggle, when you fail, when you encounter difficulty. Ease and fluency produce minimal neuroplastic change. Educational research confirms this repeatedly. Students who study in comfortable conditions, with material presented clearly and logically, report high confidence in their learning. But they perform poorly on tests. Students who study in difficult conditions, with material presented in confusing or challenging ways, report low confidence. But they perform significantly better. The difficulty itself produces learning. This is deeply counterintuitive because your subjective experience is backwards. When you're actually learning, it feels like you're failing. When you're merely recognizing familiar patterns, it feels like you're understanding. Your brain lies to you about what constitutes real thinking. So genius-level thinkers have learned to invert this relationship. They seek out confusion. They deliberately approach problems from unfamiliar angles. They strip away the vocabulary and techniques they already know and try to rederive everything from scratch. They treat ease as a warning sign. Consider how Einstein developed special relativity. He didn't start with advanced mathematics. He started with a paradox he'd noticed as a teenager. If you chase a beam of light at the speed of light, what would you see? According to Maxwell's equations, you should see a stationary electromagnetic wave, frozen in space. But Maxwell's equations don't have any solutions for stationary waves. Something was wrong. Most physicists at the time tried to resolve this by adding complications to the theory, inventing concepts like luminiferous aether to make the mathematics work. Einstein did the opposite. He went back to the most basic assumptions underlying physics. What is simultaneity? What does it mean for two events to happen at the same time? Everyone assumed this was obvious, that simultaneity was absolute. Einstein questioned it. If you accept that light speed is constant in all reference frames, which Maxwell's equations require, then simultaneity cannot be absolute. Events that are simultaneous in one frame occur at different times in another frame. Time itself is relative. Space is relative. Only space-time, the combined four-dimensional structure, is absolute. This conclusion emerged not from complex calculation, but from simple, relentless logical analysis of basic assumptions. The method was to question what everyone else accepted as obvious, and by doing so, a deeper truth about physical reality was revealed. You can train yourself to do this, not to Einstein's level perhaps, but to a level dramatically beyond ordinary thinking. The method is systematic. First, identify the assumptions embedded in any problem or concept. Every field has tacit assumptions that practitioners accept without examination. In classical physics, absolute time was such an assumption. In biology before Darwin, the fixity of species was such an assumption. In economics, perfect rationality is such an assumption. These assumptions become invisible precisely because everyone accepts them. Training your brain to see them requires conscious effort. Second, question each assumption explicitly. Why do we believe this? What evidence supports it? What would happen if it were false? Most assumptions cannot survive this scrutiny. They're convenient simplifications, historical artifacts, or unexamined intuitions. When you expose them to direct logical analysis, they dissolve. Third, rebuild the concept from more fundamental principles. What can you verify directly? What follows logically from verified facts? What requires additional assumptions? And are those assumptions justified? This process is slow. It's difficult. It feels inefficient because you're doing in hours what textbooks accomplish in paragraphs. But the understanding you gain is qualitatively different. It's flexible, robust, transferable. Let me give you a concrete example from mathematics. Everyone learns calculus by memorizing rules. The derivative of x squared is 2x, the integral is the antiderivative, and so forth. These are patterns to recognize and apply. But what is a derivative actually? What is it measuring? A derivative measures instantaneous rate of change. But what does that mean? How can something have an instantaneous rate when a rate requires change over time? This is the paradox that confused mathematicians for centuries. The answer requires understanding limits. As the time interval approaches zero, the average rate of change approaches a specific value. That value is the instantaneous rate. The derivative is the limit of a ratio as the denominator approaches zero. Now you understand what a derivative is, not just how to calculate one, and this understanding transfers. You can apply the same logical structure to any situation involving rates of change in any field because you comprehend the underlying concept rather than just the symbolic manipulation. This is what forcing your brain to think like a genius means. It's not about being smarter. It's about being more thorough, more skeptical, more willing to question the obvious and rebuild from fundamentals. It's a discipline, a habit of mind that anyone can develop through practice. But there's a deeper level to this that we need to examine. First principles thinking is necessary, but not sufficient for genius-level reasoning. You also need to develop what physicists call physical intuition, the ability to feel how systems behave before you calculate anything. The greatest minds in physics had this to an extraordinary degree. They could look at a problem and immediately sense the right approach, the relevant variables, the approximate answer. This wasn't magic. It was pattern recognition at a much higher level, built from thousands of hours spent thinking deeply about physical systems, building mental models, checking those models against reality. Here's the apparent paradox. I just told you to distrust pattern recognition, to always rebuild from first principles. Now I'm saying you need to develop sophisticated pattern recognition. How do you reconcile this? The answer is that genius-level thinking operates on two modes simultaneously. You use first principles reasoning to build deep, verified understanding of fundamental mechanisms. Then you use that understanding to construct accurate mental models, reliable intuitions that let you reason quickly about complex systems. But you never trust those intuitions blindly. You always have the option to drop back down to first principles and verify. Think of it like learning to play chess. Beginners calculate every move by analyzing possible sequences. This is slow but thorough. Masters recognize patterns instantly. They see that a position is strong or weak without conscious calculation. But if you examine how masters develop those patterns, you find they spent years analyzing positions deeply, checking their intuitions against reality, correcting errors. Their pattern recognition is reliable because it's built on verified understanding, not on superficial associations. The same applies to any domain of knowledge. You develop reliable intuition by repeatedly checking your guesses against rigorous analysis. When your intuition proves wrong, you don't ignore it. You examine why it was wrong, what your mental model was missing, how reality differs from your expectations. Then you adjust your model and try again. This is active learning, and it requires a specific approach to feedback. Most people avoid negative feedback. When they're wrong, they feel embarrassed or frustrated and move on quickly. Genius-level thinkers do the opposite. They seek out their errors because errors reveal gaps in understanding. Being wrong is information, and information is valuable. The first principle is that you must not fool yourself, and you are the easiest person to fool. Your brain desperately wants to be right. It will distort evidence, ignore contradictions, rationalize failures, anything to maintain the comfortable feeling of understanding. Fighting this tendency requires conscious discipline. Here's a practical method: prediction testing. Before you solve a problem, predict the answer. Force yourself to commit to a specific prediction based on your current understanding. Then solve the problem rigorously. If your prediction was wrong, stop. Don't just note the error and continue. Analyze why you were wrong. What did your mental model predict? Why did it predict that? What aspect of reality did your model fail to capture? This process is uncomfortable because it forces you to confront your mistakes directly, but discomfort is information. It tells you where your understanding is weakest, where you need to rebuild from first principles. Let quotas work through an example. Imagine a spinning ice skater. She pulls her arms in and spins faster. Why? Most people say conservation of angular momentum and consider this an explanation. But it's just a label. What's the actual physical mechanism? Angular momentum is the product of rotational inertia and angular velocity. When the skater pulls her arms in, she decreases her rotational inertia because mass is now distributed closer to the axis of rotation. If angular momentum is conserved and rotational inertia decreases, angular velocity must increase. She spins faster. But why is angular momentum conserved? This is the deeper question. It's conserved because there's no external torque acting on the skater. But why does absence of torque mean conserved angular momentum? Because angular momentum is the rotational analog of linear momentum, and momentum is conserved when there's no external force. This follows from Newton's laws, which themselves follow from the symmetries of space and time. Now you're seeing the full logical chain from observation to fundamental principle. The skater spins faster because of spatial symmetry. That's the deep answer. Everything else is intermediate mechanism. This kind of analysis takes time. It feels excessive. You might think, why not just accept that angular momentum is conserved and move on? Because that superficial understanding is brittle. It doesn't transfer to new situations. It doesn't reveal connections to other phenomena. It doesn't let you derive novel results. When you understand that conservation laws arise from symmetries, you suddenly understand why energy is conserved due to time symmetry, why momentum is conserved due to spatial symmetry, why all conservation laws have the same fundamental origin. You see the unity underlying apparently disparate phenomena. This is what physical intuition actually is, the ability to see deep connections that aren't obvious on the surface. Developing this requires what I'll call aggressive curiosity. Don't accept any explanation as final. Always ask the next question. Why is that true? What causes that? What would happen if conditions changed? Push every chain of reasoning back to the most fundamental level you can reach. Then push a little further. Most people stop too early. They reach a point where the explanation feels satisfying and they stop questioning. Genius-level thinkers have learned to distrust that feeling of satisfaction. It's often premature. There are deeper layers to uncover. Consider thermodynamics. Heat flows from hot to cold. Everyone knows this. But why? The standard answer involves entropy, the second law of thermodynamics, statistical mechanics. These are correct but still intermediate explanations. The deepest answer is probabilistic. There are vastly more microscopic configurations corresponding to thermal equilibrium than to thermal disequilibrium. The system evolves toward equilibrium because that's overwhelmingly likely, not because of any force or tendency in the conventional sense. This understanding only emerges if you keep asking why. Why does entropy increase? Because there are more high-entropy states. Why does the system explore all possible states? Because of quantum mechanics and the ergodic hypothesis. Why does quantum mechanics work that way? Now you're at the frontier of human knowledge, asking questions we haven't fully answered. But reaching that frontier, recognizing the boundaries of current understanding, is itself valuable. It shows you what we actually know versus what we assume. It reveals opportunities for new discovery, and it prevents you from fooling yourself into thinking you understand something when you've merely memorized an explanation. Now we arrive at the most subtle aspect of genius-level thinking, something that separates truly original minds from merely competent ones. The ability to hold multiple contradictory models simultaneously and to know when to use each one. Physics provides the clearest example. Light behaves like a wave in some experiments, and like a particle in others. Classical mechanics says particles have definite positions and velocities. Quantum mechanics says they don't. General relativity describes gravity as curved spacetime. Quantum field theory describes it as the exchange of gravitons. These models contradict each other, yet all are useful in appropriate contexts. Ordinary thinkers find this disturbing. They want one correct answer, one true model. They view contradictions as problems to resolve. Genius-level thinkers view contradictions as information about the limits of each model. They learn to use whichever model is most appropriate for a given situation, while remaining aware that all models are approximations. This is complementarity, a principle that applies far beyond quantum mechanics. Reality is too complex to capture in a single model. We need multiple perspectives, each revealing different aspects of the truth. The skill is knowing which perspective to use when, and understanding how they relate to each other. The greatest physicists exemplified this. They developed multiple formulations of the same theories, formulations that looked completely different but gave identical predictions. Both were correct, but each made certain problems easier and others harder. They could switch between them fluidly, choosing whichever provided the clearest path to solution. This flexibility requires deep understanding of the foundations underlying each model. You can't switch perspectives if you've only memorized procedures. You need to know why each model works, what assumptions it makes, where it applies, where it breaks down. This knowledge only comes from first principles analysis. Here's how to develop this capacity. When you learn any model or theory, immediately ask what it doesn't explain, what phenomena fall outside its scope, what assumptions is it making, under what conditions would it fail. Then seek out alternative models that cover the same territory from different angles. In physics, study both Lagrangian and Hamiltonian mechanics. Both describe classical motion, but they emphasize different aspects. In biology, understand both genetic and ecological perspectives on evolution. In economics, examine both microeconomic and macroeconomic frameworks. The contradictions and tensions between perspectives are where the deepest insights hide. This brings us to the final element: comfort with uncertainty. Genius-level thinkers don't need to have answers. They're perfectly comfortable saying, "I don't know," or "We don't understand this yet." They distinguish clearly between what's established, what's probable, what's speculative, and what's completely unknown. Most people blur these categories. They treat hypotheses as facts, uncertainties as certainties, ignorance as knowledge. They do this because uncertainty is uncomfortable. The brain craves closure, definite answers, confident conclusions. Resisting this craving requires discipline. The greatest minds in science were famous for this intellectual honesty. When asked about interpretations of quantum mechanics, about what's really happening at the quantum level, they would say, "We don't know. We have a mathematical formalism that makes accurate predictions, but we don't have a clear physical picture of the underlying reality, and that's acceptable." Science doesn't require us to understand everything. It requires us to make accurate predictions and to know the limits of our knowledge. This intellectual honesty, this refusal to pretend understanding where none exists, is perhaps the most important characteristic of genius-level thinking. It's what prevents you from fooling yourself. It's what keeps you searching for deeper explanations. It's what makes genuine discovery possible. So how do you force your brain to think like a genius? You develop a specific set of habits. Question every assumption, especially the ones that seem obvious. Rebuild concepts from first principles rather than accepting surface explanations. Embrace difficulty and confusion as signs of actual learning. Test your understanding by predicting outcomes before calculating them. Analyze your errors to reveal gaps in your mental models. Push every chain of reasoning back to fundamental principles. Learn multiple perspectives on the same phenomena. Distinguish clearly between what you know and what you assume. Accept uncertainty without discomfort. These are trainable skills, not innate gifts. They require consistent practice. They feel unnatural at first, because your brain is optimized for efficiency, not for truth. But over time, with deliberate effort, first principles thinking becomes automatic. Physical intuition develops. The ability to see deep connections emerges naturally from thorough understanding. The remarkable thing is what happens next. Once you've trained yourself to think this way in one domain, the skills transfer. The habit of questioning assumptions, of rebuilding from fundamentals, of seeking multiple perspectives, these apply everywhere. Physics, mathematics, engineering, philosophy, art, even daily life decisions. The method is universal because it's based on how reasoning itself works, on what constitutes genuine understanding versus superficial pattern matching. You begin to see reality more clearly, not through any mystical insight, but through disciplined analysis. You notice things others miss because you're asking questions they never think to ask. You solve problems they find impossible because you're willing to go back to foundations they take for granted. You make connections they don't see because you understand mechanisms rather than just outcomes. This is what genius actually is. Not superhuman intelligence, not divine inspiration, just human reasoning, taken seriously, applied thoroughly, pushed to its natural conclusions. It's available to anyone willing to do the work, to endure the discomfort, to question the obvious and rebuild everything from scratch. Nature reveals her secrets not to the brilliant, but to the persistent, to those who refuse to accept easy answers and who keep asking why until they reach bedrock truth.